In mid-February 1943, a single American tank rolled to a stop in the Tunisian desert near Sidi Bou Zid. Its hull was coated in fine North African dust, its white star partially obscured by a hastily applied German cross. This was War Daddy II, an M4A1 Sherman, serial number USA 3067641, built by Lima Locomotive Works and assigned to Company G of the 1st Armored Regiment, 1st Armored Division. Captured intact during the chaotic aftermath of the Battle of Kasserine Pass, it had just completed a 350-kilometer journey across some of the most unforgiving terrain in North Africa. For 4.5 days, personnel from a German reconnaissance unit drove it relentlessly, over rocky wadis, through scorching heat, across roads cratered by artillery and mined by retreating Allied forces. The engine never overheated. The transmission never slipped. The final drives held without complaint. To the officers of Heavy Panzer Battalion 501 who gathered around it, notebooks already in hand, this machine was more than a battlefield trophy. It was a contradiction. Here was a tank the Americans built by the tens of thousands, supposedly underarmored, undergunned, and technologically crude, and yet it functioned with a quiet, unbroken reliability that defied every assumption the Wehrmacht held about armored warfare. Within weeks, War Daddy II was loaded onto a cargo ship bound for Germany. The Army Ordnance Office had issued strict, unequivocal orders. This tank must reach the testing facility at Kummersdorf intact and fully operational. Not for propaganda. Not for scrap. But for truth. At the Kummersdorf Proving Grounds, 25 kilometers south of Berlin, the most meticulous engineers in the German military awaited. They would not merely inspect this Sherman. They would dissect it, stress it, compare it against their own Panther and Tiger prototypes with scientific rigor, and document every finding in exhaustive technical reports. What they discovered over the next 2 years would not be a revelation of American genius, but of German blindness, a systemic failure to grasp that in modern industrial warfare, reliability is not a secondary trait. It is the foundation of combat power. The mathematics of armored warfare were about to be rewritten, not through superior firepower or thicker armor, but through something the Germans had never prioritized: automotive excellence that simply refused to break. The Sherman's powertrain told the story first. German tanks, from the Panzer III to the Tiger, relied on straight-cut gears in their transmissions, precise, powerful, but unforgiving. These gears demanded exact alignment, perfect lubrication, and flawless driver technique. A misshift, a moment of fatigue, or even a sudden jolt over rough terrain could cause teeth to shear under load. Repairs required factory-level tools, specialized training, and hours of labor, resources rarely available at the front. The Sherman, by contrast, employed herringbone-cut gears, a design standard in American automotive manufacturing since the 1930s. These gears featured angled teeth that engaged gradually, distributing stress across multiple contact points simultaneously. The result was smoother operation, greater tolerance for driver error, and far longer service life under sustained combat conditions. German engineers had considered herringbone gears too complex for mass production given their industrial capabilities and workforce training. The Americans, however, had been stamping them out by the tens of thousands for over a decade. To them, it was not innovation, it was routine. Then came the transmission itself, 5 forward speeds, with synchromesh on gears 2 through 5. This eliminated the need for double clutching, a skill German tank drivers spent weeks, even months, mastering. To operate a Panther effectively, a soldier needed the hands of a pilot and the patience of a watchmaker. What they discovered over the next 2 years would not be a revelation of American genius, but of German blindness, a systemic failure to grasp that in modern industrial warfare, reliability is not a secondary trait. It is the foundation of combat power. The mathematics of armored warfare were about to be rewritten, not through superior firepower or thicker armor, but through something the Germans had never prioritized: automotive excellence that simply refused to break. The Sherman's powertrain told the story first. German tanks, from the Panzer III to the Tiger, relied on straight-cut gears in their transmissions, precise, powerful, but unforgiving. These gears demanded exact alignment, perfect lubrication, and flawless driver technique. A misshift, a moment of fatigue, or even a sudden jolt over rough terrain could cause teeth to shear under load. Repairs required factory-level tools, specialized training, and hours of labor, resources rarely available at the front. The Sherman, by contrast, employed herringbone-cut gears, a design standard in American automotive manufacturing since the 1930s. These gears featured angled teeth that engaged gradually, distributing stress across multiple contact points simultaneously. The result was smoother operation, greater tolerance for driver error, and far longer service life under sustained combat conditions. German engineers had considered herringbone gears too complex for mass production given their industrial capabilities and workforce training. The Americans, however, had been stamping them out by the tens of thousands for over a decade. To them, it was not innovation, it was routine. Then came the transmission itself, 5 forward speeds, with synchromesh on gears 2 through 5. This eliminated the need for double clutching, a skill German tank drivers spent weeks, even months, mastering. To operate a Panther effectively, a soldier needed the hands of a pilot and the patience of a watchmaker. Even more telling was the air filtration system. North African sand was fine as talc and insidious in its ability to infiltrate engines. German tanks, particularly the early Panzer IVs and Tigers, suffered chronic clogging of air filters, leading to premature engine wear and frequent breakdowns. The Sherman's oil bath air cleaner, a design borrowed directly from commercial trucking, handled the dust with remarkable efficiency. Every system on the tank reflected a design philosophy that prioritized practical functionality over theoretical optimization. It was not built to impress on a specification sheet. It was built to keep moving. But the true test came not in the controlled environment of a workshop, but on the hill. On June 6 to 7, 1943, at the Hillersleben artillery range, Reich Minister Albert Speer convened a major armament conference for senior Wehrmacht officers, industrial executives, and technical directors. The demonstration program included hill climbing trials designed to compare German and captured Allied tanks under identical conditions. There, War Daddy 2 sat alongside a brand new Panther IV, fresh from the man factory, and a Ferdinand tank destroyer, representing the pinnacle of German armored vehicle technology. Speer, personally accountable to Hitler for armaments production, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration would provide answers neither he nor German tank designers wanted to acknowledge. The Sherman climbed the test slopes smoothly. Its driver shifted through the synchronized gears without hesitation. The engine maintained consistent power delivery throughout the ascent. The vehicle handled with confidence, demonstrating the ease of operation that would become a Sherman hallmark. The Panther followed, its 700-horsepower Maybach HL-230 engine roaring under strain. It matched the Sherman's performance, but only barely, and with visibly greater difficulty. The Ferdinand, massively heavy at 65 tons and powered by a complex electric transmission system, stalled halfway up the incline. Recovery crews scrambled to restart it as Speer watched in silence, surrounded by dozens of senior officers and industrial leaders. The embarrassment was profound. In his post-war memoirs, Speer would recall Sherman reports from his October 1944 inspection tour of Italy. Reports on the cross-country mobility of the Sherman had been very favorable. The tank climbed mountains German tank experts considered inaccessible to armor. He attributed this to the Sherman's very powerful motor in proportion to its weight, giving it cross-country mobility, definitely superior to German tanks. The 26th Panzer Division had specifically reported this advantage. These observations from Germany's armaments minister carried significant weight within Wehrmacht circles. Publicly, the Nazi press downplayed the implications. Das Reich newspaper, in a carefully worded article on June 27, 1943, described the Sherman as one of the special accomplishments of the North American laboratories, and a quite praiseworthy product of the North American steel industry. It noted the tank's serial construction and its fulfillment of The almost arrogant requirements of the North American automobile industry. The piece even acknowledged the Euro-stabilized gun as the first attempt of its kind ever to be made anywhere, recognizing American innovation in fire control. These statements, crafted to avoid appearing defeatist, nevertheless concealed the private alarms spreading through German engineering departments. American tanks weren't just adequate. They were fundamentally better engineered for sustained field operations. Back at Kummersdorf, systematic testing continued through the summer and into autumn of 1943. Engineers measured the Sherman's operational range, conducting extended trials that pushed the vehicle to its limits. They documented operational ranges exceeding 2,000 kilometers before requiring major maintenance, roughly 4 times what early model Panthers could achieve in actual field conditions. They measured transmission efficiency that exceeded any German tank, with power losses through the drivetrain significantly lower than comparable German systems. They examined the synchronized manual transmission that made gear changing smooth and simple, requiring neither the double clutching nor the careful rev matching that German transmissions demanded. The final drives presented another revelation that challenged German engineering assumptions. Panther tanks employed final drive systems inherited from the Tiger design, a configuration prone to catastrophic failure under stress. The design used straight-cut gears and housings that proved structurally inadequate for the loads imposed by the 45-ton vehicle. German mechanics in North Africa and on the Eastern Front had reported final drive breakdowns so frequently that Panthers were often abandoned after relatively short movements, sometimes less than 100 kilometers. The Sherman's final drives, built using the same herringbone gear principles as the transmission, rarely failed, even under sustained combat conditions that would destroy German components. Restoration projects decades later would find Sherman final drives that needed no mechanical restoration after years of storage, testament to design margins that exceeded immediate requirements by substantial factors. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated through Wehrmacht technical branches. These documents, intended for senior officers and armaments ministry officials, painted a sobering picture of comparative capabilities. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked, despite its theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training. While German vehicles required factory-level precision and specialized equipment for many repairs, the entire American design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive on paper but couldn't be maintained in combat. This industrial maturity flowed from a deeper source: civilian experience. Before the war, the United States had over 26 million automobiles, nearly 1 for every 5 citizens. Car ownership was commonplace across all economic classes. Mechanic skills were widespread, supply chains robust, and manufacturing standards honed by decades of commercial competition. Germany, by contrast, had fewer than 500,000 civilian vehicles in 1939. Automobiles remained luxury items for the wealthy and Nazi Party elite. The Volkswagen, people's car, promised to German workers since 1934, had delivered fewer than 1,000 units by the outbreak of war. This vast difference in automotive industry maturity translated directly into tank design philosophy. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already possessed. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. The comparison became impossible to ignore as field reports accumulated through late 1943 and early 1944. Panther tanks required strict operational restrictions to prevent mechanical failures that would leave them stranded. Drivers received explicit instructions not to change gears frequently, as excessive shifting damaged the transmission. Third gear, in particular, broke so often that field manuals warn against its use except when absolutely necessary. Panthers could not turn while backing up, as this would destroy the transmission. Pivot turns were only possible when ground resistance was equal on both tracks, severely limiting tactical flexibility. Foreign objects entering the running gear could jam the drive sprocket, requiring hours of maintenance to clear. These problems existed despite Panthers being built in dedicated tank factories by skilled workers using the best available materials Germany could provide. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford, and Chrysler, men who had spent decades perfecting mass production for the civilian market. They applied those same principles to military requirements. The tank incorporated commercial automotive components wherever possible, leveraging existing supply chains and manufacturing expertise. The transmission came from multiple manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company, all building to identical specifications with fully interchangeable parts that could be mixed freely without adjustment. This standardization, routine in the American automotive industry, remained largely theoretical in German tank production, where each manufacturer, Daimler-Benz, MAN, Henschel, introduced subtle variations that prevented true parts interchangeability. A Panther built in one factory often required different spare parts than one built in another, crippling logistics and maintenance at the front. Additional captured Shermans arrived at Kummersdorf through 1943 and 1944, including tanks taken from British units in Italy and Soviet forces on the Eastern Front. Each underwent similar testing protocols, building a comprehensive database of American tank capabilities across different variants and production periods. The British had refitted some Shermans with their 17-pounder anti-tank gun, creating the Firefly variant that addressed the Sherman's main weakness in firepower. German engineers examined these modified tanks with particular interest, noting how the Sherman's large turret ring accommodated the significantly larger gun with minimal structural modification. The Firefly demonstrated growth potential built into the original design, something German engineers had not considered when specifying their vehicles. The Panther, rushed into production to counter the Soviet T-34, had no capacity for significant armament upgrades without complete turret and vehicle redesign. Its internal volume was tight, its turret ring small, its powertrain already overstressed. The automotive testing program expanded to include reliability trials specifically designed to replicate combat conditions. Engineers drove Shermans through hundreds of kilometers of cross-country movement, recording every mechanical incident, maintenance requirement, and component failure. They compared these results with field reports from Panther and Tiger units operating on the Eastern and Italian fronts. The numbers told an unambiguous story. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic rates as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 in 5 tanks were actually capable of combat operations. By comparison, Sherman tanks maintained substantially higher operational availability across all theaters, typically 80 to 90%, even under harsh conditions. Specific data from German field reports documented Panther reliability problems in devastating detail. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness, more tanks lost to mechanical failure than to enemy action. By December 1943, readiness had improved to only 37%. February 1944 reports showed 37% operational. April 1944 reached 50%. May 1944 finally achieved 78%. These figures represented the percentage of Panthers actually capable of combat on any given day. The remainder were broken down, awaiting parts, or undergoing repairs. The progression showed gradual improvement as design flaws were addressed, but even the best Panther readiness rates never matched what Shermans achieved from initial production. By December 1943, the pattern had become undeniable to any objective observer. Engine lifespan for the Sherman diesel variant, M4A2, exceeded 3,000 kilometers under proper maintenance. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers, presented as a success. This improvement merely brought Panther engines to roughly one-third of Sherman diesel capability. Sherman transmissions required minimal maintenance between overhauls, with synchronized gears that made driver error less likely to cause damage. Panther transmissions demanded constant attention and frequent repair, with third gear failures so common that drivers learned to skip from second to fourth gear to avoid using the problematic ratio. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation. Field reports from German units using captured Shermans reinforced the Kummersdorf testing data with real-world operational experience. German mechanized units, desperate for reliable vehicles as their own tank inventory degraded, eagerly employed any captured American tanks they could obtain intact. Unlike Soviet T-34s, which Germans modified extensively before use, Shermans entered German service without changes. They didn't require modification because they worked correctly as designed, with no fundamental flaws that needed correction. German tank crews who had experienced multiple mechanical failures in their own vehicles found the Sherman's reliability remarkable and frequently commented on it in letters and reports. Reports from Panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions before mechanical failure immobilized their vehicles. The 10th SS Panzer Division captured 12 M4A3 Shermans at Hillersleben in January 1945 during Operation Nordwind. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German assault. The 12 Shermans were formed into the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war. They served as reconnaissance vehicles and mobile reserves, roles that required sustained movement without maintenance stops and reliable mechanical performance. German commanders recognized what Kummersdorf testing had proven years earlier: American tanks could be relied upon to function when needed. This dependability, more than firepower or armor protection, determined tactical utility in the final months of the war. A Sherman arriving at the battlefield with an operational gun was infinitely more valuable than a Panther with superior firepower, broken down 20 kilometers behind the lines. January 1944 brought expanded testing programs as Wehrmacht forces retreated across multiple fronts and additional captured equipment reached Kummersdorf. Engineers examined the M4A1 with the Continental R975 radial engine, documenting its characteristics and comparing it to other variants. They tested the M4A2 with twin General Motors 6046 diesel engines, noting its superior fuel efficiency and different operating characteristics. They evaluated the M4A3 with the Ford GAA V8 gasoline engine, which American crews considered the best Sherman power plant. Every variant demonstrated the same fundamental characteristic: excellent automotive reliability derived from sound engineering principles and consistent manufacturing processes. The consistency across variants impressed German engineers, who were accustomed to significant quality variations between different manufacturers producing nominally identical vehicles. The diesel-powered M4A2 particularly impressed German engineers at Kummersdorf. Soviet forces received over 4,100 of these tanks through Lend-Lease, and significant numbers fell into German hands during retreats on the Eastern Front. The twin GM 6046 diesel engine provided performance matching any Sherman variant while consuming substantially less fuel than gasoline engines, a critical advantage as German fuel supplies dwindled. German designers had experimented with diesel tank engines but abandoned the effort due to manufacturing difficulties and the complexity of fuel injection systems. American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules, demonstrating manufacturing flexibility and technological sophistication that German industry never achieved during wartime conditions. March 1944 brought reports from General Heinz Guderian, Inspector General of Panzer Troops, noting in official communications that improvements to Panther reliability had achieved what he termed acceptable standards by early 1944. Engine life had reached 700 to 1,000 kilometers, and final drive problems had been largely resolved through design modifications and improved manufacturing processes. This improvement, presented as a significant success in German military communications, merely brought Panther reliability to a level the Sherman had achieved from initial production in 1942. The German army celebrated reaching standards that American tanks had exceeded from the beginning, highlighting how far behind German armored vehicle development had fallen. The comparison grew more painful as German tank production struggled with increasing resource shortages and Allied strategic bombing. Allied bombing campaigns targeted key bottlenecks in the Panther and Tiger production chain with increasing effectiveness. The Maybach engine plant in Friedrichshafen suffered severe damage from Royal Air Force Bomber Command on the night of April 27 to 28, 1944. The raid involved 322 aircraft, and is described in Imperial War Museum archives as the most damaging raid on German tank production of the entire war. The attack also destroyed the ZF gearbox factory adjacent to the engine plant. Production of tank engines and transmissions halted completely for 6 months. When production finally resumed in November 1944, quality control had degraded significantly. Slave labor, increasingly employed in German tank factories as German workers were conscripted for military service, introduced deliberate sabotage, cigarette filters jammed in oil passages, gaskets installed incorrectly, components assembled without proper clearances. These problems never affected Sherman production, safely located in American factories far from any combat zone and staffed by motivated workers earning good wages under decent conditions. The fundamental difference between American and German tank production lay not in engineering knowledge but in industrial capability and underlying design philosophy. German engineers understood automotive principles as well as their American counterparts, possessing extensive theoretical knowledge and scientific expertise. They simply never applied those principles consistently to tank design, instead prioritizing other factors. German tanks emphasized performance characteristics that made for impressive specifications, high-velocity guns, thick sloped armor, but poor reliability in field conditions. The Panther's powerful 75mm KWK-42 gun and thick frontal armor came at the cost of an overtaxed powertrain that couldn't reliably support the vehicle's 45-ton weight. The Tiger's formidable capabilities demanded complex maintenance procedures and frequent repairs by highly trained specialists. These trade-offs might have been acceptable if German industry could produce enough vehicles and enough spare parts to maintain them. It could not, particularly as Allied bombing intensified and raw material shortages worsened. American engineers, trained in automotive mass production through decades of civilian industry experience, designed tanks that could be manufactured by the tens of thousands and maintained by mechanics with basic training using skills learned in civilian life. The Sherman powertrain used components proven in commercial service, with design principles borrowed directly from automobile and truck manufacturing. The electrical system included a backup generator that could power turret traverse even when the main engine stopped, a feature that seemed like unnecessary luxury to German designers but proved invaluable in combat. German tankers could only dream of such conveniences, particularly those who had experienced their turret traverse failing when engines stalled on slopes. These features didn't appear in German technical specifications because German designers had never considered them high priorities compared to armor thickness and gun power. By spring 1944, Wehrmacht units on all fronts reported increasing mechanical problems as manufacturing quality degraded and spare parts became increasingly scarce. Panthers required transport by rail for movements exceeding 100 kilometers because their final drives couldn't survive sustained road marches. Field commands issued explicit orders restricting Panther movement to preserve the vehicles for actual combat rather than losing them to mechanical failure during approach marches. The Berge Panther recovery vehicle, built on a Panther chassis to recover disabled Panthers, shared the same reliability problems as the tank it was supposed to recover. German commanders faced the grim reality where mechanical failures eliminated more tanks than enemy action, with some units reporting that 70% of tank losses were due to breakdowns rather than combat damage. Meanwhile, Sherman production continued at unprecedented rates that German industry could never match. American factories produced 49,324 Sherman tanks during the war, more than all German tank production of all types combined. British Commonwealth forces received thousands through Lend-Lease. The Soviet Union received over 4,000 diesel variants. Chinese forces in Burma used Shermans to devastating effect against Japanese armor that was technologically inferior to both American and German designs. Every theater where Shermans served confirmed what Kummersdorf testing had revealed. Properly maintained Shermans kept running under conditions that would disable or destroy German tanks. German tank crews who captured and used Shermans universally praised their automotive excellence in letters, reports, and post-war interviews. Reports from the Eastern Front noted that German mechanics found even the complex Chrysler A57 multibank engine, with its 5 separate engine blocks, easier to troubleshoot compared to German tank engines that required specialized knowledge and equipment. The Ford GAV8, praised by Allied crews for its exceptional reliability and power output, seemed remarkably dependable to German mechanics accustomed to Maybach engines that required constant adjustment of valve clearances, ignition timing, and carburetor settings. The General Motors twin diesel, which the U.S. Army had rejected as less reliable than gasoline engines and relegated to Lend-Lease production, far exceeded the performance and reliability of any diesel engine German industry had produced for tank applications. The Sherman's generous design margins provided another advantage that German engineers came to appreciate. The basic transmission and final drive components originally specified for the 30-ton M4 with 400 horsepower required no major modification to handle the 42-ton M4A3E8 Jumbo assault tank with its significantly increased armor protection. The same components that powered the standard Sherman successfully transmitted 650 horsepower from experimental engines without failure or need for reinforcement. German engineers tended to calculate that such overbuilding represented waste, excess capacity that increased production cost and used scarce materials without immediate benefit. American engineers understood that margins provided growth potential for future upgrades and battlefield reliability that made the extra investment worthwhile over the vehicle's service life. By summer 1944, German tank commanders facing the Allied invasion in Normandy knew their technical disadvantages extended far beyond individual tank capabilities. American artillery superiority, devastating close-air support, and overwhelming logistical capacity combined to overwhelm German forces regardless of tank specifications or tactical prowess. But the Sherman's reliability meant American armored units could sustain continuous operations that German panzer divisions simply could not match. American tank battalions could launch attacks, sustain combat operations, conduct pursuits, and immediately prepare for the next operation without extensive maintenance halts. German panzer divisions had to carefully husband their limited operational vehicles, calculating that every movement consumed precious remaining component life and brought mechanical failure closer. The difference in operational availability determined which force could maintain offensive pressure, and which had to carefully ration its limited combat power. German use of captured Shermans in combat operations provided final proof of American automotive superiority from the German perspective. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, attempted to obtain captured American vehicles to disguise their operations. German planners wanted Shermans specifically because of their reputation for reliability. However, the brigade received only 2 Sherman tanks, and only one proved serviceable enough for operations. The serviceable Sherman never actually saw combat due to massive traffic jams that prevented the infiltration operation from achieving its objectives. In an operation requiring vehicles to function without breakdowns while operating behind enemy lines far from any support, only American equipment offered reasonable chances of success. German tanks, even when fully operational, couldn't guarantee the sustained performance such missions required. January 23, 1945, brought the final official admission of German automotive failure. A meeting of the Panzer Commission produced a report documenting catastrophic final drive failures across all German tank types. The document's findings were devastating. Prior to the 1945 Eastern Offensive, there were 500 defective final drives in the Panzer IV, 370 in the Panther, and roughly 100 in the Tiger. Additionally, approximately 200 failures had been reported in the Hetzer tank destroyer based on the Czech 38T chassis. General Wolfgang Thomel, Chief of Staff to the Inspector General of Panzer Troops under Guderian, explained the operational impact in stark terms. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles and in some situations abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. German tanks, built to intimidate through impressive technical specifications, failed in the most fundamental requirement of armored vehicles: mechanical reliability sufficient to reach the battlefield and complete missions. Kummersdorf testing facility prepared for evacuation in early 1945 as Soviet forces advanced relentlessly toward Berlin. Engineers frantically packed testing data and shipped documentation to facilities farther west, hoping to preserve technical intelligence for post-war analysis. Some of the captured tanks, including at least 2 Shermans, were pressed into improvised service with combat units desperately defending the approaches to Berlin. These vehicles fought alongside German designs in the final desperate battles, providing one last comparison under actual combat conditions. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out. The German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even experienced crews accustomed to poor reliability. The story of War Daddy II and the dozens of other Shermans tested at Kummersdorf represents one of the great industrial disparities of World War II. German engineers, working within an industrial system that prioritized theoretical perfection over practical utility, produced tanks that looked impressive on paper but failed in sustained field operations. American engineers, applying decades of automotive manufacturing experience to military requirements, produced tanks that lacked technical sophistication in many areas but worked reliably under conditions that defeated German equipment. In armored warfare, as in most military operations, the weapon that functions when needed beats the weapon that might be theoretically superior, if it could only reach the battlefield and complete its mission. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed. Systematic examination of destroyed German tanks found mechanical failures as common as combat damage as causes of loss, final drives broken from stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded them to the critical importance of reliability and maintainability. They built tanks that no conscript mechanic could maintain without extensive specialized training, powered by engines that demanded constant expert attention from skilled technicians, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units. The lessons learned through testing at Kummersdorf directly influenced German tank design thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 tank incorporated many design philosophies that had made the Sherman successful: robust powertrain with substantial design margins, easy maintenance requiring minimal specialized tools, standardized components enabling rapid field repairs, and growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The captured Shermans at Kummersdorf, including War Daddy II with its distinctive name still painted on the hull, represented far more than enemy equipment brought home for technical examination. They were tangible proof that industrial maturity and sound engineering principles based on practical experience mattered more than theoretical technical innovation pursued without regard to manufacturing reality. German tank designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority. They were wrong. American tank designers built reliable vehicles because they understood through hard experience that logistics, maintenance capability, and sustained operational availability determined victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between Sherman and German tanks influenced not just tactical armored warfare but fundamentally shaped the broader understanding of military industrial capacity and its decisive role in modern conflict. Germany entered World War II with technical advantages in many weapons systems, possessing scientific knowledge and engineering expertise that exceeded most opponents. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production, while simultaneously fighting enemies on multiple fronts. The United States entered the war with weapons that were less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality, reliability, and performance based on combat feedback. This industrial approach, perfectly exemplified by Sherman tank design and production, proved far more effective than German technical sophistication applied to small-scale production. The United States produced nearly as many Sherman tanks as Germany produced tanks of all types combined, while also producing enormous quantities of every other weapon type, supplying allies through Lend-Lease, and maintaining the highest standard of living among all combatant nations. This economic performance, impossible to match for Germany even before strategic bombing intensified, decided the war's outcome as certainly as any battle. The mathematics were simple and brutally clear when examined objectively. A Sherman with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy or required 3 days of maintenance for every day of operations. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt. Reliability wasn't just a convenience factor or secondary consideration. It was the foundation of operational effectiveness, determining whether armored units could execute their assigned missions. German tanks consistently failed this fundamental test throughout the war. American tanks consistently passed it. Kummersdorf testing had proven this beyond any reasonable doubt by mid-1943, even as German commanders continued deploying Panthers and Tigers that looked fearsome and possessed impressive specifications, but couldn't be relied upon to function when needed most. The Sherman tank didn't win World War II through technical superiority in firepower or armor protection. It won through industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance. German engineers at Kummersdorf understood this by mid-1943 based on their exhaustive testing. They wrote detailed reports documenting their findings. They tested the evidence repeatedly with scientific rigor. They reached the correct conclusions about American advantages. But understanding a problem and solving it are fundamentally different challenges. German industry lacked the capacity to retool production around reliability principles while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition and simply extended those mature principles to military production with remarkable success. War Daddy 2, that single Sherman tank captured in Tunisia and tested exhaustively at Kummersdorf for months, told the entire story through its mechanical reliability and consistent performance. Every kilometer it drove without failure was evidence that German tank design had taken a fundamentally wrong path by prioritizing specifications over reliability. Every test that demonstrated American automotive excellence was proof that industrial maturity and practical manufacturing experience mattered more than theoretical performance calculations. Every comparison between Sherman and German tank reliability proved that Americans had solved problems German engineers didn't even realize they needed to solve. The tank itself was unremarkable in many ways, just one of 49,000 produced. What it represented was devastating to German confidence, proof that Germany had already lost the industrial war even as fighting continued, and that American productive capacity could not be matched regardless of German technical sophistication or tactical skill. In the end, the battlefield was not the only arena of decision. The factory floor, the assembly line, the design bureau, these too were theaters of war. And in that war, War Daddy too spoke the truth that no German general could silence.